Okay, so thanks everybody for attending today. So today we've got a talk from Dr. Geoff Vasil from the University of Sydney. So Geoff did his PhD at the University of Colorado before doing postdoc work in Toronto and at the University of California. He was a DECRA from maybe 2014 to 2017 at the University of Sydney. Where he's now a senior lecturer. He's also the driving force behind the Daedalus library, which is, am I pronouncing that right? I know it's a Greek goddess. Yep. So, which is a suite of tools for the solving PDEs using various sorts of spectral discretizations. And it looks like he's going to be giving us a very interesting talk today, somewhere on the interface between continuum and discrete dynamical systems. So, thank you very much, Geoff.
Yep, thanks for having me.
Oh, actually, I'm sorry. Before Geoff starts, Geoff's very happy to take interjections along the way. So if you do have any questions, don't hesitate to just drop them in the chat box, and we'll take those along the way as we go.
Great, yeah. And yeah, that's right. And I'm bad at noticing them, so please notify me if there's something. Okay, so I'll just jump in. I'll share my screen, I presume. And let's go with that. There we go. There we go. Okay, so do we see a screen?
Yes, we do.
Okay, that's great. Okay, we'll see. Okay, we'll see how this works because I don't have a mouse now. Okay, we'll see how it goes. Okay. Actually, let me. Okay, so I see if I make my screen full screen. All right, let me do this again. We're sharing. Right, so right now you guys can see the whole keynote, I guess.
That's correct.
Okay. Okay, let's do this. Yeah, once I'm in, I lose my mouse, and then there we go. Okay, we should be. Oof. Okay. One more try. Okay, get that out of there. Okay, I think we're good to go. All right. So this talk, mechanics of a large pendulum chain. A bit of background. This actually was a whole research project that I started because I was looking down the barrel of a gun in my mathematical computing course, needing to give the students something to do that was more interesting than you usually get, but still comprehensible and tractable for undergraduates. And I worked something out, and I'll discuss that in a bit. But then I said, hey, this is actually pretty fun. And so I started doing some work on it myself. In fact, yeah, I give it to my students every year, and I tell them if anybody comes up with any brilliant ideas, we'll put it on a publication, which I have yet to complete, hopefully one day soon. So mechanics of a large pendulum chain. And I wrote this talk for the first time about a year ago. I'm from the geophysical, astrophysical, fluid dynamics community, and they have a workshop every summer, except for this summer, for the first time in 50-something years, in Woods Hole, and the geophysical turbulence, or geophysical fluid dynamics program in Massachusetts. For anybody who is out there who does GFD or hasn't heard of it, please contact me and I can tell you all about it. It's wonderful. But it's basically summer camp for math nerds. And I gave this talk a year ago to people who are very knowledgeable about geophysical fluids. This talk is not about geophysical fluids per se, but I made a lot of references to things that I expected people in the room would know. I will try to elaborate a bit more, given that this is a general audience. So GFD is this subject of atmospheres, oceans, of course, planets, stars. And really, if I were to give a list of 2 items that really characterize geophysical fluid dynamics, it's a study of highly vortical, mostly incompressible turbulence, highly multi-scale phenomena of a high Reynolds number, and gravity-restored waves in a stratified medium. And then there's, of course, other waves. There's rotationally restored waves and so on, but gravity is really, you got to have gravity if you want a planet. This is just a still image of a movie that I couldn't find. So, but this is exactly, this is from a simulation of a star. You see lots of overturning turbulence on the top in this case, and then exciting waves below. And this is an upside down version of essentially what happens in the Earth's atmosphere. For example, in the troposphere where we live, you get lots of convection and turbulence. And then in the stratosphere where airplanes fly, you don't have strong turbulence, but you do have waves. And when you experience what we call turbulence in an airplane, you're experiencing mostly those waves. And so this is in a nutshell the phenomenology of geophysical fluid dynamics that people have spent more than a century trying to understand, and it's very hard. But you know, we're always looking on the lookout for simplifications of this system. So hang on a minute, I'm going to check here. I see that there's a notification. Where am I? Uh-oh. Hold on. I'm having trouble all of a sudden. Okay. Chat. Let me see here. I've got 3 chats. Okay, cool. Those were before this all started. I apologize. Back I go. Okay. So I am going to, so the motivation here is to try to study a very simple system, something that is, you know, way fewer degrees of freedom than three-dimensional fluid at very high Reynolds number, and still has a lot of the properties that you would want. Now, model systems. Okay, so there are there's two-dimensional turbulence. That was actually a movie that you saw of two-dimensional turbulence. Well, actually, I think that was three-dimensional. But a 2D slice is a common approximation. In 2 dimensions, there's a problem that vorticity is conserved in 2 dimensions, and that leads to things being quite different in some ways than in full 3 dimensions. You have inverse cascades and a lot of other phenomena that you don't have in 3 dimensions. And until I thought of this, I couldn't think of any really good one-dimensional analogs of of vortical turbulence. Okay, so there's a Berger's equation, Berger's turbulence, or Bergulence as it's called, and this is a very compressive kind of turbulence, right? It might be a one-dimensional model of a bunch of shock waves, but things that are allowed to spin around, it's not obvious how you can have things spinning when they only depend on one dimension, right? That's kind of it seems obvious that that can't happen, but in some ways maybe it can. So a large pendulum chain. Now also I am a parent of 2 young children, 2 toddlers, and I spent quite a lot of time at the playground. And about a year ago I was in Massachusetts and I was at the playground, as I am most Saturday mornings. And I said, hey, wait a minute, I can make a movie of this. So here is some phenomenology of the mechanics of a large pendulum chain, recorded by me at the park. Now, this isn't a whole lot to look at as it is, but you can learn a lot more by slowing it down and watching it again. And you can see a few things happening right away. So one is that there's a large coherent motion to the swing, right? It's what you would call sort of a coherent state. But that coherent state is unstable to sort of a whipping motion. And the whipping motion puts small scale waves into the chain, which cause these waves to bounce back and forth. And eventually these waves remove energy from the large scale coherent motion. There is, of course, real friction in the chain with the links and such, but what it's really doing is it's breaking apart the large-scale motion, the coherent motion, and dissipating it on small scales. And if you wait just a bit longer, the swing stops moving. So we've seen a few things, right? Large scales go to small scales. We see the interaction of wave-like behavior with rotational dynamics. And so that's something to be on the lookout, right? And this is obviously, for those that know, very characteristic of a lot of geophysical phenomena. Okay, so I like to be pedagogical in some of these things, so I will be pedagogical. You can solve simpler problems even in this chain, even in the one-dimensional chain where you whip it around. We can look at various simple solutions and learn a little bit about what's going on. And in fact, in all kinds of fluids, one of the things you're oftentimes interested in are what are the waves present in the fluid independent of the strong nonlinearity. So you linearize around some state. In this case, if you have a chain that's just hanging perfectly straight down, gravity pulls on that and leads to a tension in that. the wave equation for a string with a given density and a tension is the equation at the top. I can't use my mouse and point at it, but there it is at the top. And you can easily work out what the tension is. It's just the force from the mass hanging below a certain point on the chain. And so that's gravity times the density times what is left. You can get a wave equation of this form. It's got a non-constant coefficient. It's a great undergraduate PDEs problem. I recommend it. This is, you can solve it using the separation of variables in time and space. And you get, if you do a transformation of the variables, Bessel's differential equation. So this is also an interesting historical note that actually Bernoulli was the first person to solve this problem in this way that I'm showing you. And he encountered this differential equation, which 100 years hence was called Bessel's differential equation, because Bessel rediscovered it in the modes of a drum, right? So that's another good PDE's problem. And this, of course, there's a singularity at the endpoint, so there's no boundary condition there, but there is a boundary condition at the top of the thing. You can pin the top, or you can slide it around or whatever, and then that decides on what the discrete modes of the string are, and you get essentially quantized modes. The dispersion relationship, the relationship for the frequencies of your chain are related to the roots of this Bessel function, and gravity and the length of the chain. And it's really fun. You can actually solve these things. You can actually calculate these modes. I bring in my chain to class, and we shake the chain around, and you can see these shapes, at least a couple of them. The higher order ones are hard to get, but you can time it. I have a student will time it, and it'll swing back and forth at the right time scale, and so on. And I happen to have a chain which is actually 1 meter long, so it makes everything nice. Gravity is 10, L is 1, 2 is 2, and so on. So this is pretty fun. So you're already seeing, though, that a hanging string under gravity supports wave-like dynamics. Okay, so that's an important feature of this. Yeah. Okay. There's just another point about this. Now, this was interestingly the study of an Ig Nobel Prize. It was awarded to this man called Joe Keller. And Joe Keller, photos, there's 2 photos of him. He won 2 Ig Nobel Prizes, so I have 2 photos of him. Was, of course, until he died a couple of years ago, I would say the preeminent applied mathematician of maybe the latter half of the 20th century. I mean, he was a real giant in many areas. Wave dynamics, asymptotics, you name it. And I gave this to this crowd at GFD, a Geophysical Fluid Dynamics workshop, and Joe was well known to many of the people there. So actually, the picture on the left is a picture of Joe sitting on the porch at Walsh Cottage, and the picture on the right was a picture from his New York Times obituary that was unknown to many people my age or younger. The old timers, of course, knew Joe looking like this as well. Joe won his own Nobel Prize for this, one of them, for determining why is it when a woman with a ponytail, or a man with a ponytail, I suppose a person with a ponytail runs, and the ponytail bounces vertically, does it begin to swing horizontally? And this is an example of a parametric instability. So if you vibrate something with a frequency close to twice its resonant frequency, then you get a mode which grows with a growth rate proportional to the amplitude and the frequency. And here's my 1 meter long chain. I'm trying to excite maybe one of the higher order waves, and so on. So there's been work on this in a lot of areas. If you look for hanging chains and papers about this stuff, you hear everything. So Joe Keller, I don't think was thinking about geophysical fluid dynamics, even though that was a big interest of his when he did this study. But I wish he were alive that I could tell him that I think it actually relates to this as well. So what's more also is I really want you in particular to look at the picture on the right, okay, the older photo. That's a very significant photo for reasons that I will come back to later. I just want you to remember that picture. Joe really is giving something away, very significant in that photo. Okay, so this idea of a parametric resonance is also universal notion in, well, gosh, everything, right? But geophysical fluid dynamics. So if you can even make your chain even simpler and think of it as a pendulum, right? Which is only one single link of your chain. And you can think, if I, rather than shake it side to side, if I actually if I can change the length and the gravity of the pendulum. So I imagine taking my string and I attach it to a little pulley and I pull on the string and I make it shorter and longer, then you can write out a general equation for the pendulum, and you can solve that under some approximation and show that that you will get instabilities as a result of length changes or gravity changes. And this is the mechanism by which nonlinear tides are excited on planets and stars. You have a very weak perturbation from the moon nearby, but that's changing the local gravity and the local size, the depth of your layer by some amount, and this leads to these moderately large amplitude tides. Okay, so there we go again, same thing, and you can in fact take tides and by some like brutal approximation actually get out the equation for pendulum, and it's really the same mechanism. They really are analogous systems. Okay, so how do we formulate the problem? So this is again meant to be a bit of pedagogy, but let's get time here. Okay, good. So the mechanism that you really need to formulate these problems, in my mind, is you need to use Hamilton's principle of least action. You need to use the Euler-Lagrange equations, and it's really difficult to just sort of guess what the force is on this swinging chain with these inextensibility conditions on it. So interestingly, I like to point out that the Euler-Lagrange equations, the equations that you use once you have the Hamilton's principle, predate Hamilton's principle by quite a long time. So we're going to be using this. And I'm going to go through this briefly. I know this is simple, but there's a point to it. So, okay, if we have a pendulum, but there's no stick, no rod, we just have a mass that is falling under gravity, right? So that's the 0th order pendulum. And in that case, your Lagrangian is your kinetic minus potential energy. Potential energy is the height times gravity. You do your Lagrange equations, you get that the momentum in the horizontal direction is conserved. You get that the momentum in the vertical direction responds to gravity. You can solve this, and you get what is the high school physics problem, right? Ballistic motion, right? You can throw a ball, what goes up must come down. If you drop something, it falls, right? It's as simple as it gets, right? So this is obviously not a pendulum, but it does show some of the dynamics that we're looking for. So how do you use it? So the only thing that's really happening is gravity is the only game in town, with one other player, which is the length of the pendulum, right? So now you have the same problem. The Lagrangian is the kinetic minus potential energy, but there's a constraint which says that the distance to the origin has to be fixed, right? So this thing can slide around in a circle. So x squared plus z squared is equal to the length squared of the pendulum. So now you minimize the Lagrangian, but you only minimize it over the constrained paths, right? So you and there's two different ways to solve this. And this is something that, again, will apply to this chain problem. Option one is you can solve the constraint. So you can say, I can find out that x squared plus y squared or plus z squared is true if x is equal to L times a cosine angle and z is L times a sine angle, something like that, right? Or you can use the method of Lagrange multipliers. You can add a term to the Lagrangian that enforces the constraint. And then there's another option, which is you could use both. And I'll explain using both is actually superior to using one or the other. So, okay, option 0, solve a constraint. So you write down a trigonometric form of your position. You then minimize your Lagrangian over the angle only, and you get the pendulum equation, right? The second derivative of the angle is equal to minus the sine of the angle with gravity over length. Option 2, a bit more interesting, very powerful method, use the Lagrange multiplier, right? So this is what you do when you can't solve the constraint, what I previously did. In that case, you say that there's C of x constraint, which is equal to 0 when you're on the track. And you create a new variable called tau, in this case, a Lagrange multiplier, and you just make a new Lagrangian. When you're on the constraint, C is 0, and when you're off, you penalize it, right? And so now you just treat tau as if it was any other variable of the system, and you minimize over it. If you differentiate with respect to tau, you get your constraint back. Now when you differentiate with respect to your trajectories, you get a term which has tau in it. Okay. So now there's three equations, right? So there is the constraint, of course, and now there's looks like something that looks like a bit of a harmonic oscillator. X double dot is minus the tension times x. You have three equations for three variables, and we have to solve that. A key fact about Lagrange multipliers is that there's always a way of turning your two equations with Lagrange multiplier and eliminating the time derivatives. So there is a single linear instantaneous equation where if you know your trajectory, I can tell you what the Lagrange multiplier is, and that's an important principle. Okay, so you can solve the Lagrange multiplier, and you find some nice properties that the Lagrange multiplier turns out to be the tension in the rod, and the tension is greater if you're swinging around faster, and the tension is greater if you're in the direction of gravity rather than you're up against gravity. Okay. And then option two, all of the above, in this case doesn't really help that much, but you can solve the dynamical equations in the variable form, and then you can solve for the tension. The tension doesn't couple back to the problem, but it does later on. Okay, so again, that's a little pedagogical. This is recorded. Hopefully you can go back and look at the slides if this is not that clear. But this is really powerful when you want to solve multiple constraints. Okay, so a single pendulum there is on the left, a double pendulum, let's say, on the right. There's the lengths are the same. In this case, they could be different. You have multiple constraints. No, there's one constraint for every single link. And so if you try to go and plow forward by solving the constraints, you can do it. Okay, it turns out, right, that the distance between any given points is one. In this case, I'll set it to be one. And so you can write the distances as a sum of trigonometric series at the top. And then you put those into your kinetic energy term, and you get a all-to-all coupling between the velocities, the local rotation velocities. You get this giant matrix with a double sum, and that's bad news if you ever want to try to do large numbers, right? That'll just lead to these giant matrices that you have to deal with. It's a mess, okay? So the Lagrange multiplier approach is you say, I now have a tension in every single link, and I put it on as a constraint. Is this way. When you do this now, it's, as we know, right, the only way a given link knows about anything is it knows about its up neighbor and its down neighbor, but it doesn't know about the neighbors that are 17 units away, only indirectly via transmission through the chain, right? So now you can see that if you do this, you get the acceleration of every single mass is equal to this finite difference approximation. It's not an approximation, it's exactly finite difference formula in terms of the tension and the distances of your neighbors.
Can I ask a quick question, Geoff?
Yep.
If you solve for the constraints rather than use Lagrange multipliers, does that avoid the need for an elliptic equation? It
does.
Okay, thanks.
But it involves, but you're not saved because it requires the inversion of a giant matrix, which is worse than an elliptic solve if you want.
Yeah.
So you're kind of hosed no matter what, basically, right?
Yeah.
But if you're going to solve and essentially what you've got, you have an instantaneous condition, and so you need to solve that one way or the other. Basically, is the moral of the story. So yeah, I want to be clear that solving this elliptic equation, as you say, in this case is far better, and you'll see why, than doing it some other way. And again, for fluid dynamics, this is again very similar to the vorticity, stream function formulation versus sort of normal velocity, pressure formulation, things like this.
Cool, thanks.
Cool. Okay, so you have this nearest neighbor coupling, but we don't know what the tension is, okay? But remember I told you, and as was alluded to, there is a constraint. So now you solve the constraint, okay? So this is due both at the same time. So we have this set of coupled equations. Now we know what the constraint solution is. We put that in and we substitute it in. We do a lot of algebra. And we end up with, after rearranging stuff, a very clean system. So what you've got is for the velocity is the time derivative of every angle. And the time derivative of every velocity is a nearest neighbor coupled system involving the differences of the angles, the sine of the differences of the angles, and then the differences of the tensions, but only to your nearest neighbors, right? So that's the top set. And then there is a elliptic equation, indeed, which is an equation for your tension at every point, which is this finite difference-like thing that is sourced by the rotation rate and the gravitational term, right? So those are the two things. And it really has a very PDE-like behavior of a boundary condition at the first row of your system, and then you have a bunch of equations which are the interior of your chain, right? You can abstract this, okay? So abstracted, it then looks in sort of a vectorial form. You have theta dot is omega, fine. Omega dot is a d of theta acting on your tension variable. It's a little thing to fix up gravity at the endpoint. And then you have an L of theta times your tension is equal to this, how fast everything is spinning. The D is very much like a gradient. It's an antisymmetric thing where if sine is, let's say, 1, which is not always, but if it were, then you would have 1 minus 1, 1 minus 1. It'd be like a centered finite difference derivative. And if cosine was equal to 1, which it's not, you would have something that looks like a Laplacian, right? So this is a trigonometrically weighted derivative in Laplacian, okay? And it's tridiagonal, symmetric. So solving L is really a snap, okay? So this was the innovation that allowed this to happen numerically quite a lot faster than before. So if you look, people have solved chain problems up to hundreds or even 1,000 links, and they're always doing it using this giant coupled matrix, and they can't get very far. And when you're doing it like this, you can really push to much larger sizes and do decently big sizes things pretty quick. Okay, so here's what we've all been waiting for. So this is what it looks like, right? So this is 1,000 links. So everything I've explained to you before is sort of what I would explain to students, and then tell them, okay, code this up, solve these linear algebra stuff, make a time stepper, and play. That's kind of the student project. So let's play. Okay, so there's 1,000 links. The links are too small to see, and I'm just going to take this thing and I'm gonna just drop it, and we're going to watch what it does. Okay, so here we go. Whoop, there we go. So it only moves in 2 dimensions in this case. So we see quite a few things happening, right? So clearly, like the swing at the playground, it goes back and forth. It bounces, and it's exciting smaller scale waves on the along the length of this, and the swinging motion has slowed down quite a lot, and it's more or less bouncing quite a lot now. We see some cool emergent behavior. So first of all, there is no technical friction in this, right? So I'm not including a frictional term. The equations conserve energy, and you can check that. They do very well. It's also completely inextensible, right? So this thing is, by mathematical construction, not allowed to become longer than its total length. If this was hanging straight down, it would be 1 unit of length, but you can see that it's in fact coiled itself up and has excited quite a lot of very fast, small-scale degrees of freedom that are whipping around on this thing that has damped the swinging motion, and then over a longer period of time damped out the bouncing motion. And if you wait long enough, this thing will just be fluctuating around an equilibrium, just sitting there. So this is, as they say, it has thermalized. Okay. so it's a brilliant statistical mechanics problem. It's reached some equilibrium state after some transients, and the fluctuations are quite large in this case, sort of square root of n fluctuation, square root of 1,000. It seems to be moderately larger than that, actually. I mean, it seems like, I mean, these are maybe 20% fluctuations, 5%, I don't know, but it's a pretty vigorous system, and there's a lot to study with this stuff. Okay, so yeah, this runs for quite a long time. Excuse me. You can look at some diagnostics, right? So you can look at, for example, the angle of the swinging motion relative to the vertical, and you can see here that it starts off at some high angle relative to its initial condition is basically 1. It swings, it almost gets back up as high as it started to do. It oscillates down, and then it actually quite rapidly collapses, right? So if you were to trace the plot at the top left, you might think it would decay slowly, but it decays slowly, and then kaboom, it's gone. And that's the expectation of strong additional degrees of freedom, right? So transferring nonlinear degrees of freedom from one mode to another, can lead to some very abrupt behaviors. The bouncing motion, as we observe, takes longer to damp out, right? So it's the blue curve, and then after these things settle in, there's some statistical fluctuation which persists for very long times. So I see there's a couple of questions.
Sorry to interrupt, Geoff.
Yeah, please.
Got a question here from Sai, who's asking if the links can decrease in length.
Well, it can't. The individual links cannot change their length. They're one unit always. But what it does is it's locally, and you'll see this in a minute. It's all folding itself on top of itself, right? So that's how the overall chain, the center of mass of the chain, can move from its initial length. It folds itself all in a ball, right? So the thing can end up, you can fold it like a jackknife, right? And it could be, the whole chain could be folded into one unit, but unextended, it's 1,000 units, right? So,
okay.
So that's the idea here.
Thanks.
I just had a quick question.
Yep.
In terms of this nonlinear cascade you're seeing there, the sort of high frequencies, are you using an energy conserving integrator, or do you use?
No, not explicitly. No, I'm not. I kind of, so it's because of the formulation of the equations, that's actually hard to do. It's not impossible, but it would require some more monkeying around to get that to work just right, because the equations are not a canonical Hamiltonian system.
Yeah.
But that's doable. And for this case, I tend to not like energy conserving integrators, because you can then check the energy in an energy conserving problem, and if it's wrong, you know your integrator's wrong. So it's a good check for accuracy. But I've run harder problems with up to 10,000 links, and even with really small time steps, it doesn't tend to conserve its energy. And for reasons I don't understand, I don't know if it's a bug at those for some larger scales. I don't know what's going on actually. So my plan is to actually try an energy conserving integrator at some point, but I haven't gotten around to doing that.
So do you have some dissipation that you've added, or does the time integration scheme just dissipate by itself?
Yeah, so I'm using a high. So the swinging damping motion is not a numerical effect. Right? So the damping motion is the thermalization. So the global energy is conserved to a very high degree, 10 to the minus 6 or something like that. And you're just taking energy out of the large scales and putting it into the small scales.
Yeah.
Does the time stepper dissipate? It will by a little bit, 10 to the minus 6 or so. I'm using a high order Runge-Kutta method to do this.
Yep.
Right? So one of these adaptive ones where you can kind of keep track of how you're going.
Cool, thank you.
Yeah. So, okay. So this is the cool thing. We are seeing friction, the birth of friction, the birth of temperature, right? We're seeing a system which is energy conserving, frictionless, develop the same properties as a system that has friction. Okay. And at least in this case, it's not numerical. So what's going on? Okay. So I like entropy. Who doesn't like entropy? It's a very mysterious thing. Here's a nice point I like to make. So on the left, we have a guy, Leo Tolstoy, and he said all happy families are alike, and all unhappy families are unhappier in their own way. This has become a moderately well-known quote these days. It's used in the introduction of many business books, I suppose, or something like that. It's used to describe exactly what Tolstoy was trying to get across. And it occurred to me a while ago that it is a perfect encapsulation of the concept of entropy, which is not something that I've heard very much about, right? So most of the time, people who are using this are describing entropy in many words, but they're not saying that really this is entropy. And what is entropy? It's simply the statement that there are many more ways to be messy than there are to be clean, right? Or there are a larger number of configurations that are sort of random than there are configurations that are not random, right? So if you're going to bet on something, bet on randomness, because there's way more ways for you to be random, right? There's way more ways to have a dirty kitchen than there are to have a clean kitchen. If I randomly move a book off of my bookshelf to somewhere else, it will probably not end up in a nice place on my bookshelf. If I randomly move a book from somewhere on my floor, it will probably not end up on my bookshelf, and so on, right? So this is the idea that there are unhappiness is a state of high entropy, and happiness is a state of low entropy. There's very few ways in which you can rearrange your situation and still remain happy, right? So Tolstoy said this, but the thing I especially also like is that that Boltzmann and Tolstoy said this in the same decade. Okay, so that's another point that has not been made yet. So I like to think that perhaps this was an idea who was philosophically floating around in the 1870s, basically 1860s perhaps. And I think it'd be an interesting history project to determine, what philosophers was Tolstoy and Boltzmann both reading? Did they both know certain influential writers and whatnot? Did they know each other, for all I know? So that'd be an interesting historical thing. And if you dig in a bit more, you find I'll need to edit. I need to copy. I need to get out of here because I can't actually read it. So I'll just read it right here. To elicit the laws of history, we must leave aside kings, minstrels, and generals, and select for the study the homogeneous infinitesimal elements which influence the masses. So that's from War and Peace. That's another very statistical mechanics kind of view, right? The idea of we shouldn't worry about all the individual. You should aggregate over lots of individual things, and then that'll tell you what really is going on, right? The damping motion is essentially democracy, if you want. And then likewise, I would say Boltzmann had kind of rather Tolstoy-esque point of view of available energy as the main object at stake in the struggle for the existence and evolution of the world, right? So politics and love and war and all these interesting things, really all come down to basically fighting over energy and entropy, really, and fighting over that. And another way to say this is anything you buy, anything you ever purchase, you are either purchasing a decrease in the amount of entropy for yourself or your increase of the amount of entropy for your adversaries, right? So you either pay somebody to clean up your room, or you pay the military industrial complex to put heavy firepower downrange and create lots of entropy for your adversaries. So there's this interesting concept, and so studying it in this chain is a nice clean system. We know everything or almost everything about this chain, so maybe this is a nice model system to study thermalization, entropy dynamics, all these kinds of other things. Okay, so I need to move my Zoom here. Nope, one more. Again, these Zoom things really take up a lot of space. Yeah, let's try that. Okay. Okay, now here is the next slide, is the most important slide of this entire presentation. And remember, there was a particular point earlier on, a particular photo earlier on, which I said, remember that photo. It'll become very important later on. And if there's a message I want everybody to go away with this next message is it. Okay, so there it is. Entropy, right? It's Joe Keller, Leo Tolstoy, and Ludwig Boltzmann are the same person. Okay, there's my theory. So remember that. It's a conspiracy, it's a cabal, entropy, okay, aliens, okay? Very, very, very important message here. Anyway, I don't know what it is about guys with receding hairlines and huge beards that did this, but there it is. Obviously, I'm being cheeky. So, okay. So what's going on? So there was a question about the length of this thing, and the idea, right, is that as this thing starts bouncing, it can raise its configurational entropy. So there can be more ways for which the chain to be folded up than there are for it to be straight. So obviously, it's going to be more likely to be folded up, right? And you can sort of see what's happening here locally. This is a movie of, if you just zoom in on one little section, this thing is just whizzing around. Locally, I allow the chain to pass through itself, which of course is not physical, but still, kind of fun. And then you can see at different places, the degree of folding of the endpoint versus of the midsection somewhere is not the same. So there's an inhomogeneous amount of entropy in this. There's an amount of temperature, which is the amount of jiggling locally there is. And the two together imply a force, which is, if I pull it out, it's going to want to come to some entropy minimization. and so it'll retract its way inward. I see there's another question, perhaps. I don't know. I can't read it, but if anybody wants to just shout out.
It wasn't a question, Geoff. I just said I thought Leo Tolstoy looked like Will Ferrell with a beard.
Yes. I should put Will Ferrell on this as well. I think that's probably perfectly apt. So anyway, so this is this idea of entropic forces. Okay, so this is some very, paint with a wide brush explanation for why this thing bounces. That it's essentially coiling itself up, and it likes to be coiled up more than it likes to be straight. Okay, so this is a little technical. Let's see here. How are we doing on time? Okay, we're doing good. So this was something that I did last year or so, and I really haven't had a chance to do very much of in the last year. So you really should analyze this a bit more deeply. And this is a discrete system, remember. So that this is an interesting thing this is a technicality, but basically this is not a periodic system. So the Fourier transform is not particularly apt. You could make it work, but it would be kind of ugly. So you want to do some sort of, analyze this thing as a function of scale and see what's going on and see how the energy is transferring from large scale to small scale. So it turns out there's this sort of nice set of discrete polynomials called Hahn polynomials, which I like to study, and they're orthogonal, and you can sort of see them. They're a lot like Legendre polynomials, but for on integer points, and you could use these to analyze the kinetic energy spectrum, for example, of the chain. And this was a first attempt, which I haven't had a chance to do a second attempt of it. Excuse me. And it's more or less flat. This is not a very steep power spectrum like a Kolmogorov-like spectrum or something like that. I'm not looking at the potential energy part of it. I expect that if I did, this would be even flatter, maybe even completely flat. I don't know. I need to do that. Again, this is technicality, but the point is I should make is that one should dig deeper and actually look at the dynamics as a function of scale. But now just let's back up a bit. This is a fluid dynamics seminar, and I want to say, this is hopefully familiar. Hopefully things I've said have resonated. But here is the structure at the top of the equations. You have the vorticity, the rotational motion dot, the time derivative of that, is equal to the sort of a derivative of gradient-like operator acting on the tension. And the Laplacian-like operator acting on the tension is kind of like the vorticity squared, right? So this is very similar to something we've seen. So if you write Euler's equations, incompressible Euler's equations, and by the way, I'm buried into this as a condition that the lengths are inextensible, right? So there's a condition on your neighbors, how far away your neighbors are. Well, okay, so Euler's equations have, again, in this case, it's not the time derivative of the velocity, or it's velocity, not vorticity, fine. But you have the time derivative of the thing you care about is the gradient of something that's a pressure, which is the opposite of a tension, right? Rather than pulling back against you, it pushes back against you and you push on it. And if you take the divergence of this equation, you get an elliptic equation for the pressure, which is the divergence of that nonlinear term. And you can morally sort of write it as being the square of the vorticity, right? So the more the vorticity is swirling around, the more pressure perturbations you'll experience, right? So these systems are actually quite analogous, right? They both can rotate locally. There's a tension, pressure, balance. The rotational motion seeds the pressure or tension with a Laplacian-like interaction, and then there's a fixed volume for fluids and a fixed length for fixed element distance for the chain, right? So these really are a close analogy. The Lagrangian dynamics, you can do Lagrangian dynamics of a fluid. It's very similar you have a kinetic energy term, you have a Lagrange multiplier, which is the pressure, and now the condition is that the determinant of essentially the volume changes are zero rather than the length changes, right? So you can squish in all kinds of crazy ways, but you can't change the total volume, right? So if you start off with a partial fluid at some initial condition at the bottom corner of the screen and it flows up to the top of the screen, it can squish all around. And I really doubt that I drew that as a volume preserving transformation, but you get the idea. So it's really kind of same. Now, in the case of the fluid though, you need to add viscosity or else this will all go off the rails really badly, right? You'll get you'll get, it's continuum, you'll get scales at everything, you'll overrun your resolution, it'll be horrible. Whereas the chain, we actually have cut off the smallest scales, right? There is no motion smaller than a single link. So before I said everything was without explicit friction. Now you can actually just add friction. You can add viscosity to a fluid. You can add friction to the chain. And how you do this, you have to be a bit careful about it. You actually have to add some viscosity to the tension equation, or else you will not have conservation of energy or angular momentum, but it's a technical detail. And it's kind of fun to study that as well. So this is now, so here's a situation with no friction. These movies are a little janky. I should have been like higher time cadence, but hopefully you get the idea. So the case with no friction, but with a much smaller number of links, 10 links in this case, it jiggles all around, it will never stop, okay? Energy is conserved, you can check it, and it sort of thermalizes, okay? Do a high amount of friction, and what happens here is the small, the bending motion, the viscosity is like a fluid where it's a frictional motion between nearest neighbor elements. So it will damp out the small scales while leaving the large scales present. And it leads to this thing sort of swinging back and forth coherently now. And over a long time scale, the only friction is at the top pivot, and it'll take forever for this thing to wind down. If you do a medium friction, it kind of does about the same. You can see it takes a little, it jiggles around a bit more before it finally settles down, but eventually settles down to more or less the same situation. Small amount of friction, so really reducing the amount of friction. And now it really tries to thermalize a bit before it does anything. And it's able to transfer energy to small scales quicker than it was before. And when you do that, it doesn't end up in the same state. Okay, so you can see that it ends up, and remember those linear modes from the very beginning, there was the first fundamental mode, and now you're seeing primarily the second fundamental mode of the ponytail problem, Joe Keller's problem. So actually less friction in this case allowed it to damp quicker than the case of higher friction. And the same, it happens in fluids as well, right? So you need to be careful about those kind of things. And then a tiny amount of friction, it kind of acts like a small amount of friction, but it really looks quite for a while as if it was no friction at all, and then eventually you see it happen. This is kind of cool that if you watch it, you can start to see very like moderately small scale waves bouncing up and down on this thing. Once it kind of settles down a bit, you can see what you might think of semi-nonlinear waves sort of traversing and reflecting off of the top. It's kind of fun. Okay, so this is the kind of summary, right? There's this Lewis Fry Richardson notion of big whirls have little whirls that on their velocity, and little whirls have lesser whirls, and so to viscosity. So that's what we've seen. And by the way, I'd like to say again, in the spirit of universality, this of course was a quote that Lewis Fry Richardson took from a Jonathan Swift poem, which says, "Great fleas have little fleas upon their backs to bite them, and little fleas have lesser fleas, and so on ad infinitum." So there you go. There's biology for you. There's fluid dynamics for you. And I decided I like this one better. Big earls have little earls that feel animosity, and little earls have lesser earls that resent the great pomposity, right? So the same principle exists. Entropy, large scale, small scale transfer in fluid dynamics, physical system, biological system, economics and psychology and whatnot, right? So it's really a very universal principle of that things are going to, chaos happens. The things I showed you were, again, unforced. So the picture I was giving you kind of indicated that you really want to turn a propeller on and see what happens. So in this case, we do that with a long string, and it's kind of spooky. It starts jumping around, but the top is being vibrated only a very small amount, and you put energy into this thing, and it takes a while, but eventually it will start to bounce, and you'll start to settle into some sort of a state that is where the energy input and the energy dissipated by actual friction balance, and then there's some equilibrium state, and in that case, what is the spectrum? So this is the kind of things that people study for turbulence, Kolmogorov theory, and so on. And this is as far as I got about a year ago when I was last working on this. And the answer is I don't really know. I don't really know what this thing does and what kind of a spectrum it gets. I don't know if it's wants to do a Kolmogorov or not. When you have waves involved, it doesn't mean you necessarily have Kolmogorov spectrum, and so on. So there it is, just kind of more, fun food for thought. I mean, I did for fun calculate a spectrum of this, but I really, again, with the calculation was probably messing it up. But there it is. You can get these things good and get some statistically steady state. And if you've run simulations of convection or some sort of forced turbulence, these sort of plots are actually really common, right? These look very, very similar. I could take the labels off, and the kinetic energy plus potential energy, it grows, and some it saturates and it oscillates. And these things basically look very much like what you see from highly resolved turbulence simulations, right? So it's a nice model system in that regard. And then again, my first horrible attempt at kinetic energy, I literally made this when I made this presentation for like 5 minutes before the talk. And so this is almost certainly wrong, but I really meant it to just be kind of funny. But anyway, the spectrum does decrease more rapidly than it did in the other unforced case. That I do believe is true. So there you go. My conclusion is the pendulum is a stratified turbulent fluid.
Thank you, Geoff. I don't think we've had enough references to 19th century Russian literature in this series, so I really appreciate that. Just before taking questions, just wanted to say a big thank you to Sean Simon, who's been doing an instrumental job in organising this series. He's off for a position at Southampton University next week, I believe. So a big thank you to Sean for all of his work. Does anyone have any questions for Geoff? If you do, you can just drop them into the chat box or unmute your microphone. So while people are collecting their thoughts, I wanted to ask Geoff, where you had that non-canonical Hamiltonian antisymmetric matrix representation of your problem, is there a way to use Gibbons rotations to transform that into a canonical problem? And if so, does that buy you anything in terms of, is there a transformation into which you have like some sort of like, analytic or integrable solution? And also, does that allow you to build a symplectic integrator?
Yeah, those are good questions all. Yeah, so the short answer is I don't know. I haven't really given it much thought. So I don't think that, yeah, so you mean, so the Gibbons rotations would mean you would sort of take additional nearest neighbor terms to try to...
like literally, yeah, rotate the first two terms, rotate the next two down, down, down until you end up with a canonical canonical Hamiltonian.
Well, so no, the real issue here is the presence of the tension. It's that the tension itself is non-local, right? So if I wanted to eliminate the tension, so I haven't really given it a lot, so I may be saying something that's like slightly incorrect, but I'm pretty sure with symplectic integrators, you need to just have like time derivatives equal right-hand sides. That's it. And the idea that there's this internal variable of the tension that's a non-local thing, I don't really know how that works, right? So again, I haven't started really thinking about it. So the answer is maybe, and I'm sure it's something like that must be possible, but I really don't know what it is. But it's definitely not simple like nearest neighbor kind of coupling, right? Because getting really, you need to sort of think like, what is that tension really doing? And so the issue is the canonical system is the system between the angular momentum and the angular velocity. And we're really integrating here the angular velocity is another way to say it. And if you make it back in terms of the angular momentum, then it's really a big, horribly coupled system. And so I don't know. But then you said another interesting thing of symplectic, or sorry, integrable. And I'm willing to go out on a limb and say there's zero chance of this being integrable.
Right.
And the reason is that the double pendulum is not integrable.
Yeah, sure. Okay.
Right. So I think there's really no way for that to be possible.
Gotcha.
But yeah, I mean, definitely getting this thing to be numerically more stable for larger sizes would be interesting. The really hard thing is that as you go to large sizes, the time scale separation between the smallest and largest scales is ridiculous.
Yeah,
so,
right.
And so that's really what kills you on these large scales is the time scale of the smallest whirling motion. The other thing that I really want to do is do an averaging model. So I want to turn to average over the small scale whipping motion and get some sort of actual like hot wave equation basically. something I didn't talk about is you can take the continuum limit as the link size goes to 0, but you can only do it in the naive way by assuming that the links are only small. There's no folding. How to take the limit as the link size goes to 0 when you allow completely rotational motion locally. That's another challenge.
We've got a question from Eric. Do you want to unmute Eric and ask your question?
Hey, yeah, sure. Thanks for
question.
Well, I was just wondering, like, if you change the number of degrees of freedom of each link, so say it could now, each individual link can rotate in 2 dimensions, like the chain that you were,
Like
jiggling in
a
video,
yeah.
how would that change things?
Yeah. So I have to. For full disclosure, Eric is my PhD student. Thank you for showing up. But,
Hey, everyone.
I didn't plan that question. But that's right. So you can do this actually moderately easily. It doesn't even make the problem much more expensive. It's what you get is, because the number of marbles is the same, right? So your number of degrees of freedom, it's not like going from 2-dimensional fluid to a 3-dimensional fluid where you suffer from the curse of dimensionality. The number of marbles is the same. But what you get is now you get an angle where things can spin around this way, right? So rather than integrating a theta dot and omega dot, you have to now integrate a phi dot and the speed of that. So you basically have to make the system twice as large, and the tension now is exactly the same. You get more source terms to the tension. The matrix is a little more complicated, but it's basically the same structure. It goes over very nicely. There's only one catch that I can see being the case, is that you need to divide by the sine of one of the angles. I forget which one. To do it nice and clean, you essentially the system conserves angular momentum in the 3rd dimension, the one that I don't have. The angular momentum is conserved there. To get the angular velocity for that, you need to divide by the sine of an angle. And if you're dealing with in the case where the thing tends to go vertical, almost vertical, it's technically a perfectly fine limit, but I could see that numerically that could be a problem. So there are some possible numerical issues, but it in principle would be twice as expensive, not n times as expensive, and then it would probably just be infinity times more confusing, which is why I haven't done it.
Yeah, I wonder if there'd be like an analogy between adding that degree of freedom and say what happens when you heat up gases enough that new degrees of freedom in the molecules start getting involved.
That's right. And you could get instabilities. You could start it in a plane, and you could get instabilities out of plane. And we know that happens in real life, of course, right? You try to make a thing go in one. You try to make a chain swing in one line, and it won't for very long. You need to rotate with a small initial condition and so on, right? So that's right. Yeah, something would be good for a PhD student too.
Yes. Thanks.
Can you really re-express the pressure gradient forcing as temperature times entropy gradient? I hadn't thought about that.
Yeah, so that's actually really easy.
It's just a transformation of variables, right?
So wait. I'm not sure. I might have used the wrong notation, or I might have used a confusing notation. So can you rephrase your question? So,
well, I thought I saw on one of your slides that force equals temperature times entropy gradient.
Yes. Okay, that's right. Okay, that's true. Yeah, that's just the second law of thermodynamics, actually.
Yeah. Okay.
So that is just TdS equals d energy. D energy is equal to FdL, right? So that's just like work. Work is force times the distance, and heat is temperature times entropy. And so everyone here, I'll type this in the chat room. Right, so TdS.
And that's the same thing as just regular old pressure gradient, is it?
That's right. So this is what I would say. Here's a better way of there. That's what I'm looking for. The second one is correct. This is what you would say if you were to aggregate over. So you have this folded up state, and you take a little section out of that, and inside of that section, you've got a high amount of entropy, and you've got some temperature, which is local thermodynamic thermal fluctuations, and you ask about the average force on that integrated section, and the integrated length of that, right? So that's really this is after statistically averaging over chunks. You'd expect the second law of thermodynamics to hold roughly, and in that case, if you get your minus signs correct, then you get you just divide by dl, and you get F equals temperature d entropy d l, right?
Yeah. So, interesting.
And that's called an entropic force. And there's Wikipedia pages, there's YouTube videos about this. It's a really useful concept. If you take a rubber band and you pull it really quickly, it warms up. It gets hot, right? We all know that. You take a rubber glove or something like that and pull on it, it'll get warm, and that's actually what you got. And so in that case, that's adiabatic. So you're pulling on it so that the entropy is fixed inside of that. You don't allow it time to thermalize. And then the sort of flip side of this, that it gets warmer. The temperature goes up, right? So, or again, that's the same thing. If you have like a cylinder of gas and you pop the nozzle open, right? You might have been, you might have seen a CO2 cartridge or something like that that's like spewing out or something like this, like a bicycle, bicycle pump cartridge or something like that, and it gets cold because it's expanding. It's the same principle there, except for its volume and pressure in that case, rather than force and length. But it's the same principle over and over again. But this is sort of in a nutshell, you should expect the bouncing motion and sort of this oscillatory behavior strictly out of thermodynamics, which is kind of a cool idea, right? So you're using damped statistical properties to see the emergence of an oscillatory wave, which is kind of neat.
Yeah. Did anyone else have any questions for Geoff at all?
Yeah, I
yes?
have a question. It's a very nice talk and interesting topic. I enjoyed it. But in one place of your presentation, you talk about Hahn polynomials. I think I missed a little bit about what you were trying to do there. So I ask you to explain a little bit
thanks.
more.
Okay.
Also, why Hahn polynomials? Why not
Yeah, that'd be a long talk all by itself. So that was obviously where I was like, pay no attention to the man behind the curtain a little bit. But this is just a way of saying that we have a discrete system where the points on the chain, if you follow it, are all a unit distance apart.
Yeah.
And you want to use so you want to use a Fourier series. You want to basically try to Fourier analyze the fluctuations on along the length of this thing, right? Now, if you have a periodic domain, we just like take the fast Fourier transform, for example, and that's a way of projecting any given configuration onto a set of modes, each of which has some fixed number of oscillations.
Yeah.
In this case, though, we have a string with a beginning and an end, so using the Fourier transform is not a good set of functions, like sines and cosines are not a good set of functions to decompose the motions on this. They don't satisfy the periodicity condition. Okay. So that's just another way to say that there are functions called Hahn polynomials. They're polynomials. They oscillate as you might want them to, and they have a degree. The number of oscillations is the degree of the polynomial. They're orthogonal, so you can use something like a Fourier transform to decompose your motion, your configuration into some set of wiggle functions, right? So that's all it was. But it's rather too technical to kind of explain in detail. But that was just another way of mentioning that this is something I've been working on the side, and may even should have taken it out for this presentation. But yeah, that's what it is. I don't know if you've heard of Hahn polynomials before.
No, I haven't heard about it.
So I would say that as just an advertisement, they're amazing. They're really, really interesting little set of polynomials that have beautiful properties, and I can't recommend them enough. It's my favorite thing. So just Google. You won't find that much for them, but they're out there, and you know,
Yeah.
they're useful for data analysis, basically.
So should we all install Daedalus if we want to do a Hahn polynomial transform?
Daedalus doesn't actually have Hahn polynomials at this point, but it will someday soon. Yeah, Daedalus does spherical harmonics now, or very almost presently, and does all kinds of other bases. But these Hahn polynomials, Daedalus is really for continuous systems so far, and these are for discrete systems. So it's kind of, but it's an analog. It's essentially a discrete version of Legendre polynomials, really. Yeah, it was really just an advertisement for Hahn polynomials. Discovered by Chebyshev, by the way. And you know what's very significant about Chebyshev?
Mhm.
He had a giant bodacious beard. He did his work in the 1870s. So there you go, right?
Do we have we've got someone with their hand up side. Did you have a question there?
Yeah, actually, Jeffrey, I really loved the talk, and especially the reference to Anna Karenina, because I'm a fan of that book.
Yeah.
So my question is like a follow-up on the previous question, whether the links can decrease in size. So what you said was that they can rotate about the pivot, and they can fold onto each other on the neighbor. But when we look at the porch swing, so they are like these links which can, even without a fixed, they don't have a fixed pivot, so they can like kind of overlap onto themselves. So how does that like play into the dynamics of this?
Okay, I'm not quite sure I understand. So you're saying, so yeah, in this model you have two, like locally you have two sticks that can
Yeah.
do two sticks.
They can basically move across, rotate on a pivot. But when we look at the porch swing, we have these links which can like kind of overlap. So they don't have a fixed
I understand
pivot.
what you're asking about. Yeah. Okay, now I get what your question is. Somebody asked that a year ago too. I remember this now. Yeah. So the swing, yeah. So I actually happen to have two sticks. By circumstance. Yeah, that's right. So you would have this, and they can't do that. But what you're saying is like a real chain.
Yeah.
You know, if it's under tension, it does that. But they can kind of jiggle.
Yeah, exactly. So there is an additional degree of freedom.
Yeah, that would make everything much harder. But let's just put it that way, right? I mean, that would be very difficult to model. And so you're absolutely right. The chain that I showed at the beginning, it was very loose analogy for what really is what I'm studying. But that would be hard to model. It'd be doable, but you would basically need to have a condition which if they were under tension kept them where they would be.
Yeah.
If somehow they were floating up, they could do that, right? If the thing has enough tension in it, so if you get it going enough, then you might imagine that at least mostly they don't do that very much. But you're absolutely right. The other thing that would make it much harder to model, by the way, in a real chain is that it just goes through itself, right? So you could also, so people have done protein folding simulations as well, right? That's a real serious area. And in that case, they have to be able to bump into each other, right?
Yeah.
Ties and knots and stuff like that. So there's a lot of things that I haven't considered with this that would just make it really hard. So it's clearly there's a lot of fun to be had, I guess.
Yeah. And a lot of fun, with the allusions to the previous poets.
Well, I aim to please. Thank you.
Yeah, it was a really lovely talk. Thanks a lot. I enjoyed it.
Do we have any other questions for Geoff?
Yeah, I have another question.
Yep.
So if you go for 3D, how complex is it? Have you tried?
No, I haven't tried. I have not. I've written the equations down, but I haven't written a code to simulate them or anything like this. So no, I just really haven't done it at all. And I expect the unexpected. I think that, I think it'll probably be hard and there'll be like really some confusion, but then maybe, maybe because it can do this other thing, it simplifies things in other ways that I really don't know.
Yeah, it can also wobble.
That's right. Yeah, it can do all kinds of stuff. That's right.
Yes.
That's definitely on the to-do list at some point.
Yeah.
Yeah. And anybody who wants to take any of these ideas and steal them, please do. You know, give ideas away with both hands. I like to see things done, and if I want to see them done, I should be the one doing them.
Any other questions for Geoff? Well, yeah, it's 5:15 almost, so it's probably a good time to wrap things up. So thank you once again, Geoff. That was a really, really interesting talk. I thoroughly enjoyed that, and I know a lot of other people did too. Okay, well, good to hear, and I hope to see you guys in the next weeks at some point. That's right, it's in some digital medium. Okay, so thank you very, very much, everyone, and hope to see you next week.
Adios.
Adios.